Assalamu alaikum, dear students. Very glad to be back with you with another video lesson. In the previous video lessons, we did talk about the magnetic force on a charge. We did learn how to find the magnitude of that force, let's say. And then, of course, after that, we talked about the direction of the magnetic force, the direction of the magnetic field, and also the direction of the motion, or you can say the velocity. Using this three, or using the right-hand rule, of course, this three, we used to find whether the direction of the magnetic force or the direction of the magnetic field or even the direction of the motion, let's say we're an electron, not just an electron or any charged particle that that was moving inside a magnetic field. Okay, and then of course we solved some questions and then we ended up at this question right here. So we're going to continue from this point on onward, of course, and of course hopefully it is going to be as useful as the other ones as well. All right, so we have this question says, a uniform magnetic field points north if the electron moves vertically downward towards the ground, of course, with a speed of this much through a magnetic field, what force? And so basically when we talk about force, we mean magnitude and direction will act on it. If it was just what magnetic, let's say what is the magnitude of the force, it would have just found the magnitude of the force without the direction. But because it says just the force, that means you need to find both magnitude and the direction, of course. So we did learn how to find this one, of course, before, so I'm not going to resolve this one. But one thing that I'll do is basically I'll just tell you how you can determine the direction, because you can see that using or finding the magnitude is just the application of the law. Okay, so here's what it says. Remember that you're going to hold a pen or pencil in your hand like this. That is basically the direction of the motion. These are the fingers, the direction of the motion here. And then the palm of your hand would be the direction of a force on a positive charge, and then the back of your hand, the direction of the force on a negative charge. In this case, we have an electron, so you have to make sure that you focus on the back of my hand in this case here. So it says a uniform magnetic field. You can see that it basically points north here. So we have the magnetic, or you can say the magnetic field is pointing north. So if I, for example, if I use the board as, for example, a map or paper, the top of the board is going to be north, south, east, and west, and of course it is, for example, into the board that is going to be downward, you can say, and out of the board that is going to be upward here. But if I use horizontally, of course you can see that horizontally this would be north, south, and of course east, and of course there west. So we have downward and upward, that would be the back of my hand here as well. Okay, so once again, the magnetic field points north, so you have to point your hand north. Okay, but an electron is moving, or you can say moves vertically downward. If I do this, the electron is moving upward, yeah? So I'll have to flip my hand or do something about this one, yeah? So how can I do this without changing the direction of the magnetic field, just making the electron move downward, of course. In this case, I'll just flip it this way, yeah? You can see that my hands basically are still pointing north here, and the electron is moving downward. If that is the case, what is the direction of a magnetic force on an electron, guys? Don't forget, okay? So an electron is going to be the back of my hand, and the back of my hand is going to be basically west, yeah? Because you do know that north, let's say south, east, and west. So pointing this direction, that is, of course, it is west. Okay, moving on with another question here. It says an electron is moving north, encounters a magnetic or uniform magnetic field. If the magnetic field points east, what direction of the what is the direction of the magnetic force on an electron here? So can we try this one as well? I would want you to try this on your own and see if it matches the answer that I'm going to give it to you. Okay, so you done it? I hope so. Okay, so an electron is moving north, so you can align your hand is basically, by the way, this is an electron moving north. So if you align your finger to the north, that would be incorrect, yeah? So basically, an electron moving north. So this is the direction of the motion. So you can point this one to the north. I can do in many different ways. Yeah? One of the ways we can do is I can just align my hand for now like this. Yeah. So you can see that this thumb is basically pointing north. Okay. And then it says encounters a uniform magnetic field if the magnetic field points east here. So if you can see that my hand is basically pointing east, as you can see here. So the motion is north. The magnetic field is basically pointing east. So what is the direction of a magnetic force on an electron, guys? Remember, electron, the back of your hand here. So of course it's going to be upward, you can say. And another, if we are using the coordinates, we can say z positive as well. Or if I do it this way, if this is north and south, east and west, so upward, or you can say this way here, that also can become Z positive or out, or you can say out of the page as well. Yeah? But if I'm holding my hand like this, of course, it's just going to be upward in this case here. So you can say out of the page, upwards, or Z direction. These are all correct. Okay, take a look at these recited questions. These are also very important. I'm not going to do the first one, just the application of the equation, but the second one says determine the direction. So in which situation the direction of a magnetic force on a proton moves in a magnetic field is to the left of the page in here. As whenever it says to the left of the page, you already know that. In this case, you'll have to consider the paper, for example, like this. This is up, right? This is down, you can say. And this is, let's say, right, and this is the left. So in this case, the question says the direction of a magnetic force is to the left of the page, so it is in this direction. Remember, if that is on a proton, don't forget, that is going to be the palm of your hand. All right, so take a look at this one here. The magnetic field is into, let's say, the board or into the page here, and this is the direction of the motion. So the direction of a force on a positive charge, that is my palm of, let's say, so it is to the left of the page. So this is going to be the correct answer. You can say A, yeah? But let's take a look at the other ones as well. So the second one here, the magnetic field is basically moving, let's say, to east, or you can say to the right of the page here, and the motion is upward. So in this case, if I hold the pen like this, in this case, the direction of the magnetic force on a proton is going to be into the page here. What about this one here? If I do this way, you can see that the direction of a magnetic force on a proton is going to be out of the page, which in this case also incorrect because we want from to the left of the page here. What about this one here? That is basically the magnetic field is outward and the direction of the motion is to this side, or you can say to the left. So in this case, the magnetic force is going to be upward on a positive or a proton. Okay, so the only correct answer that we have now is basically option A, and of course it's going to be, figure A is going to be option D here. Okay, now we have a few study tips. So these study tips are very, very important because we're going to rely on these study tips to solve the questions that are left here, or you can say at least several questions that are coming next. Okay, so magnetic force for a charge at equilibrium, remember this. Okay, so we have a charge, and if we have, let's say, what would be the case? Let me get this back. Okay. So I want you to focus here for a moment. Let's see what is this about. Okay, so what we have, or one of the things that we have here, let's bring this one or move this one. Okay, so watch this here. It says a charge, let's say a charge to be at equilibrium, okay? So in this case we have, remember this, let's say that we have a magnetic field, okay? It doesn't matter. By the way, these are just for the sake of the example. Otherwise, it couldn't, for example, it doesn't necessarily have to be into the page, let's say. But just remember this. We've learned that when a charge, for example, goes into, let's say, into a magnetic field, of course, it experiences a magnetic force. So whenever a charge is inside a magnetic field, there is a magnetic force on the charge. Let's say if it is positive or negative, it has to be charged. That is one thing. But imagine this. We do know that this charge has a mass, even though the mass could be very, very small, yeah? This could be the mass of a proton, or the mass of an electron, let's say, or the mass of any charged particle, let's say. So, of course, we have, or it has a mass. And you do know that whenever we have, or there is a mass, this mass, of course, will be attracted or pulled downward. Do what? Due to the Earth's gravitational force here. So, of course, now there is, as long as there is a mass, of course, there will be, of course, if it is close to the Earth's surface, there will be gravitational force on that mass here. So, but you will see that sometimes it tells you that, for example, what is the magnetic force that is needed, let's say, to balance the charge. If that is the case, then in this case, we know that gravitational force would pull the charge downward. Then in this case, magnetic force has to be upward so that these two can balance one another. When we say that can balance one another, that means they must be equal in magnitude but opposite in direction. So for example, if this one pulls down the charge with 5 Newton, this one, just for the sake of an example, this one has also to, for example, push it upward with 5 Newton. So in this case, the charge will stay in the air. It will stay balanced, let's say, or it will stay hovering, let's say, above the surface or whatever. So in this case, or we can say, when the magnetic force and the gravitational force are equal in magnitude but opposite in direction, then the charge stays, let's say, balanced or at equilibrium, which means that it doesn't go down or it doesn't go up anymore. It stays at for example, at equilibrium. If that is the case, then of course we can say, right? If that is, let me keep this one on the board. If that is the case, then of course we can say the gravitational force equals to the magnetic force. So we can say the magnetic force equals to the gravitational force. But we've learned that the gravitational force, the magnetic force on a charged particle, it is equal to QVB, yes? All right, and then what is the gravitational force equals to? Remember, that is just equal to mg. But what is this m? This m is basically the mass of the charged particle, whether if it is a proton, neutron, my bad, whether if it is a proton or an electron. Remember, neutron is chargeless, so it cannot experience this. All right, and so whatever the mass is, and then of course you can find whatever that is needed, or based on this you can equalize both sides of the equation and then see or find whatever that is required. That is one thing, okay? Just remember this. When do we use this? Whenever it says the charge is balanced, or what force needed so that we can cancel the effect of the weight. Another name for this force of gravity, we can call it weight, yeah? So the force needed to balance the charge, the force needed to cancel the weight, for example, the force needed to keep the charge staying in the air. These are also viable options, you can say. Okay, so this is the first option or the first tip that we have in here. What about, for example, if it tells you that, let's erase this one here. It tells you that a moving charge, for example, or find the acceleration of a moving charge. Well, if the charge is moving, or whenever the charge is moving, let's say here's the charge is moving. We do know that after some time, the charge, not after some time, as soon as the charge goes into, let's say, into the magnetic field, it experiences a magnetic force here. But if they want you to find the acceleration of the particle, the charge is moving, yeah? If they ever want you to find the acceleration of the charged particle, obviously, whenever they say acceleration, that is basically translational force, you can say, or linear force, we can say. And if that is the case, and then for acceleration, we have, you can say F, or translational or linear speed, you can say equals to mass times the acceleration here. So whenever, for example, if assuming that a charge is moving, we want to find the charge, or let's say the acceleration of this charge, don't forget, we have, or this charge is moving inside a magnetic field, then of course we can use these two forces, or we can equalize them. We can say the force or magnetic force on this charge is basically equal to QVB, yeah? But this force, using Newton's second law of motion, equal to what? Equal to mass times the acceleration. That is the mass of the charged particle, and it is acceleration, by the way. So using this two, okay, or we can say this force is equal to this much, and this is the magnetic force here. So sometimes they ask for the acceleration. You can just use this equation to find this. What is the keyword for this? In questions, they always ask you, for example, what is, or find the acceleration of the charge, or the acceleration of the charge is this much, and then find this or that, okay? So whenever it talks about acceleration, you can use this equation here. That is the second tip that we have. Okay, what about the third one here? The third one says whenever a charge is moving in a circle. Whenever a charge is moving in a circle, do you remember unit 1? Okay. Whenever a charge is moving in a circle, of course, we have centripetal force. Okay. Of course, using okay, so watch this. We said there is a magnetic force in here, magnetic field. So whenever a charge is moving into a magnetic field, let's say, this charge, of course, it experiences a force, and then this force, or let's say the magnetic force, will make the charge move in a circle. But you've learned that whenever a charge is moving in a circle, there's always a centripetal force acting on the object. So in this case here, we can say the magnetic force, we do know that there is a magnetic force because there is a charged particle moving inside a magnetic field, equals to QVB. Okay, that is one of the things we need, of course. Okay, and then if there is movement, let's say, or a charge is moving in a circle, we do have centripetal forces as well. So if you do remember, we said one of the type of, or one of the cause of centripetal force is magnetic force. So this magnetic force causes, or basically, let's say, provides the centripetal force in here. So if that is the case, we can say this magnetic force is equal to the centripetal force as well. And if that is the case, we can say magnetic force, that is QVB, All right, QVB, and then centripetal force, you've already learned about this, equal to what? Equal to mass times, let's say, tangential speed squared divided by the radius. That is also another example, another tip that we have. We're going to use all this to solve the questions next. So one of the questions that we have is this one here. Okay, so let's solve this one together. What does it say? It says, all right, let's keep this one here. All right, we have, it says, a proton moves eastward in a plane of the Earth's magnetic equator, where Earth is, field point north and has a magnitude of 5 times 10 to the power negative 5 Tesla. What velocity must the proton have for the magnetic force just to cancel the what? The gravitational force. So we have two forces clearly. One of them is magnetic force and the other one is gravitational force. What speed is needed so that these two forces cancel one another? So we can say magnetic force equal to gravitational force, yeah? But once again, magnetic force is basically equal to what? Equal to QVB, right? And then of course equal to mg. But by the way, in this case, the mass of the electron must be given to you, proton. So proton must be, for example, or it must be either given, or you need, if you memorize this one, that would be one trouble less. Okay, so remember this. We're trying to find what? We're trying to find the velocity or the direction of the motion. But why are we using this? Remember this. Gravity, let's say this is the proton. Gravitational force, try to pull it down, but then there should be a magnetic force, and once these two, of course, cancel one another, then the magnetic force, let's say, will be at equilibrium in this case. And of course, it says, what is the velocity so that these two forces will cancel one another? In another word, what is the velocity so that these two forces are equal in magnitude but opposite in direction here? So velocity here, okay, so velocity equals to what? Equals to, we can say mg, and then divided by the charge of a proton, and then of course the magnetic field as well. The mass of the proton, guys, just remember this, yeah? That is basically 1.67 times 10 to the power negative, negative 27 kilogram, that is the mass of a proton, and then multiplied by gravitational acceleration, that is 9.81. All right, and then divided by the charge. What is the charge of proton? The charge of proton, or the magnitude of charge of proton and electron, are both equal. That is going to be 1.6 times 10 to the power negative 19. All right, multiplied by the magnetic field strength. The magnetic field strength is given, which is 5 times 10 to the power negative 5 Tesla. Okay, and then you do the math, of course, you will find the answer. That is basically going to be this much, whatever the value, it is meter per second here. All right, so this is how it is done. By the way, they don't ask for, how about the direction, for example? What happens, or what, can we find the direction of this force? Like, what direction should, actually it tells you the direction of this one, so we don't have to worry about this. But what would you do if the direction were not given, and then if they were asking you to find the direction? Simply just use the right-hand rule, and then you will be able to find the direction of the speed in this case. Okay, and then moving forward, another question which is very similar to this one here. So let's see which part is different and focus on that most. It says a proton moves at this much speed horizontally at right angle to a magnetic field. What is the strength of the magnetic field required to exactly balance the weight of a proton and keep it moving horizontally? If that is the case, to balance this immediately, that means Fg, right, or F magnetic equals to Fg, equal in magnitude but opposite in direction. And then F magnetic, that is QVB, right, Fg equals to mg here. By applying or using the information that is given, then of course you can easily find whatever that is required. So it says, what is the strength of the magnetic field here, yeah? So find B. So B equals to what in this case? B equals to mg over what? Over QV. Okay, now, this is the mass, obviously, we have a proton, so this is the mass of a proton, which is basically 1.67 times 10 to the power negative 27. gravitational acceleration or free fall acceleration, that is 9.81, and then the charge of a proton 1.6 times 10 to the power negative 19, the velocity 2.5 times 10 to the power 6 meter per second. So you'll find the magnitude of the magnetic field strength here. Magnitude of the magnetic field strength. Part B says should the direction of the magnetic field be in a horizontal or vertical plane here. Now, I want you to remember one thing here. Whenever it says there is one thing you need to focus on here. Okay, and what is this thing? Remember, whenever it says for the gravitational force to cancel, to balance, and all that, the magnetic force, or magnetic force to balance the gravitational force to cancel the weight and all that, these two forces must always be, let's say, vertical. Why vertical? Because gravity is always pulling objects perpendicularly downward, yeah? For example, if I drop this pen, will it shift to the right or left? No, it perpendicularly moves downward. So if gravity is pulling it downward, what force can we use so that it can, or what direction can we use so that it can cancel this effect? Then the magnetic force must be vertical so that it can cancel this, because gravity is downward, so magnetic force must be upward so that these two can cancel or balance one another. Okay, so of course it has to be vertical or in a vertical plane here. I think of I've messed it up here. It says, should the direction of the magnetic field, I thought it was about the magnetic force. So guys, see, please try to focus on the context of the question so that you don't fall for it, just like what I did right now. Okay, so what it talks about is the direction of the magnetic field, not the direction of the magnetic force. What I have just explained, I've explained the direction of the magnetic force on that charge. But the question wants the direction of the magnetic field. So now we have the direction of the magnetic force already, which is downward. So can we tell the direction of the magnetic field strength? We should, yeah, by knowing the direction of the speed, because we have, or the velocity here. So a proton moves this much horizontally right to a magnetic field. What is the strength of this required to exactly balance this or to move this one horizontally? So should the direction of the magnetic field be horizontal or in a vertical plane? So we don't even need actually the direction of the speed in this case. If the direction of, watch this, if the direction of the magnetic force is downward, yes? Watch this. If the direction of the magnetic force is downward, can we say the direction of, let's say, the direction of, what was it? The direction of the magnetic field, let's say, it is downward or perpendicular as well? No. If that is the case, we can say the direction of the magnetic field strength must be horizontal. So watch this. If the force is downward, okay, so you can see my hand here. If the force is downward here, so it is either this is the direction of the magnetic field or this one, yeah? So it is, these are both, we can say, in the horizontal component, but one of them could be, let's say, you can call it this side, let's say left or towards the left of the board. The other one is basically out of the board, and these are basically both horizontal. You can see in my hand, yeah? And because the magnetic force is downward. So in this case, the magnetic field must be, the magnetic field strength must be horizontal, okay? Because normally, two of them are horizontal, but yet still perpendicular to one another. Let's say this is a magnetic field, all right? Magnetic field strength, and this is the motion. These are both, you can say, horizontal, but yet still perpendicular to one another. Okay, so if I can give you another example, if you have x and y axis, for example, coordinates here, sorry, instead of holding the paper like this vertically, hold the paper horizontally. You would see that both x and y lies horizontally, yeah? So, and yet they are both perpendicular to one another as well. So in this case, to answer this question, should the direction of the magnetic field be in a horizontal or vertical plane? It has to be in the horizontal plane. Okay, another question here. I believe this is belongs to the second tip that we have. It says a proton moves at a speed of this much at right angle to a magnetic field with a magnitude of this much. Find the magnitude of the acceleration of this. So you see the word acceleration, yeah? So whenever it says find the acceleration, so we said whenever it says find the acceleration, of course, you go ahead and do or find or use the second tip that I gave you here. So let's try this one as well, real quick. Okay, so how do we find the acceleration? Let's write the information that is given. So we have speed, which is basically 2.0 times 10 to the power times 10 to the power 7, that is meter per second. Let's make the running a little bit thicker. Okay, and then at right angle to magnetic field with a magnitude, so we have B, magnetic field strength, which is 0.10 Tesla. Okay, and then find the magnitude of the acceleration of the proton, guys, remember. So we said the other tip that we have, acceleration, it is unknown. So we want the acceleration. So here's what we're going to do. We'll say magnetic force is basically equal to the force or translational or force in linear motion, let's say. That is the case, magnetic force equal to QVB. And then this force, because we want acceleration using Newton's second law, equal to mass times acceleration. So we are trying to find this acceleration here. So the acceleration, make the subject equals to QVB here equals divided by the mass of the proton. These are the protons, so the mass of the proton. So what is the charge now? Just apply or plug in the numbers. The charge of a proton is basically 1.6 times 10 to the power negative 19 multiplied by the velocity that we have is basically 2 times 10 to the power, that is 7, and then multiplied by the magnetic field strength, which is 0.10 Tesla. That is the magnetic field, and then divided by the mass of the proton, which is, once again, 1.67 times 10 to the power negative 27. Okay, that is the mass of the proton. Now do the math, of course, you will find the acceleration. So acceleration equals to this much. Use your calculator. That is going to be meter per second squared because it is acceleration. The magnitude of the acceleration of the proton. So you just, this is basically, the answer is going to be 1.9 times 10 to the power 14. Okay, now take a look at the next question here. It says the proton moves perpendicular to a uniform magnetic field, okay? B, with a speed of this much, experience an acceleration of this much in the positive x direction. What is the velocity, let's say, is, or when it is velocities in the positive z direction, determine the magnitude and the direction of the field here. Okay, so I'm not going to do the math for this problem here, but I'll do or tell you how you can do the direction, okay? All right, so, but I'll still give you the equation or like what you need to do to solve this one here. So, proton moves perpendicular to this with the speed of this much. So you have basically, you have speed, okay? And then you have acceleration, and then positive x direction, whatever. So determine the magnitude and direction of the field. Yeah, so basically find this. So you have this and this, find this one. Using this one, by the way, since or because you have acceleration, so you're going to do this one here. F magnetic equal to F in translational linear motion here, Newton's second law. So QVB equals to mass times acceleration. So basically you're trying to find the magnitude of this, find the magnitude of V first, and then what about the direction of B as well? Okay, because it says determine the magnitude and the direction of the magnetic field, basically. Okay, so now you use the math, or you do the math here, but I'll do the direction for you. So what are the directions that we have here? It says these are the speed, basically, and it is an acceleration in the positive x direction here, guys. Remember this. There is one point which is, or one thing that is very important here. We always say, for example, whenever, or the acceleration is basically always in the direction of the net force here. So when we have a net force here, okay, let's say if the net force is in this direction, let's say that there is a table here. Once you apply a force, let's say towards the right of the table, of course, if the force is in this direction, the acceleration, of course, is going to accelerate in this direction as well, yeah? So we're going to use the net force. What if there is other forces acting on this as well? But if the net force, all right, if the resultant force were acting or were to the right, of course, in this case, the acceleration will also be to the right as well, or the object will accelerate in the same direction as the force. Here, what they give you is the direction of the acceleration, not the force. But remember this, these two are basically in the same direction. So if the acceleration is towards the x positive, if that is where the acceleration direction is, of course, that means there is the magnetic forces in this direction as well, because these two must be in the same direction here. Okay, what else do we have? It says with the speed of this much. So here we have the force. It says when the velocity is in the positive z direction here. So we said into the page, that is z negative, but if it is out of the page, basically, that is going to be z positive, yes? Okay, so we have two things. This is the direction of the velocity here. Let me switch the color so that you can see better. This is the direction of the velocity. So we have two things here. We have the direction of the force and the direction of the velocity. Can you find the direction of the magnetic field? You should be able to do that, okay? And by the way, we have a proton, yeah? So don't forget that is the palm of your hand in here. So the force is basically into this direction. The velocity is basically out of the page. So how can I do this? That is basically, I can do this, okay? If I align my hand like this, basically the force is this direction, but you can see the velocity is upward. So instead of upward, I'll make it like this, yeah? So it is out of the page in this case. The velocity is in positive z, the force is in positive z direction. Excuse me. The force is basically in the direction of positive x. The velocity is outward. So what would be the direction of the magnetic field strength here? Of course, you can see that it is basically directed down of the page. If page were given, because we're using x, y, z direction here, what axis is this? That is y-axis, yeah? But which one? Is it positive or negative? That is y negative. The force is on x positive. The velocity out of, you can say, positive z direction. So this, my fingers basically are pointed towards the y or negative y direction here. All right, I hope that was clear enough. Okay, so you can see that. Or if you couldn't do that, just align your hand like this. Of course, you'll be able to do that. Okay, take a look at this question also. This is a proton travels with the speed of this much at an angle. I'll try to give you an idea about this one as well. Okay, perhaps I'm not going to do all the parts because some of the parts are just the application of the equation, which we have done it many, many times. All right. So let's do this one as well. All right, so what do we have in here? It says a proton moves with a speed of this much at an angle of 37. Here's angle is given, guys. Whenever angle is given, don't forget, whenever angles are given and you are using the magnetic force on a charge, make sure that you are using QVB sine theta. All right, so far, we haven't used this much, okay? I don't remember if we used anything, right? But remember, because angles are given here, so you gotta bring the sine theta back into the equation. Otherwise, you're not gonna get an accurate or correct calculation. Okay, so that is the case here. As you can see, magnetic field of this much points to determine the following. Determine the magnitude of the magnetic force on a proton here. So, let me write the equation for you here. So the magnitude of the magnetic force on a proton, that is going to be F magnetic here. Of course, that is going to be QVB sine theta, like I've mentioned earlier. Okay, so we have the charge of a proton, 1.6 times 10 to the power negative 19. We have the speed, which is basically 3 times 10 to the power 6 meter per second. We have magnetic field strength, okay, yes, we have magnetic field strength, which is this much. And then we have sine theta, that is going to be sine 37 degrees. And then, of course, you can find the magnetic force. That is for part A here. Okay, what about for part B? Okay, part B says the direction of the magnetic force on the proton here. So if we drew, for example, this, here's what we have basically. Yeah? A proton travels with this much at an angle of this northwest. So if that is, for example, here is the direction of the this is basically the direction of the proton movement at 37 degrees north of, or west of north, yeah? So this is north, and this is west of north, basically. This is west, this is east, and this is south, okay? So 37 degrees west of north. So north, and then the west of north, that is going to be shifting to the left side. Okay, so that is the case basically, yeah? It says, and magnetic field of this much points north. And this is basically, we can say, this is the direction of the magnetic field as well. Okay, so, but what is going to be the magnetic force on this one? Now I would like to analyze this one a little bit. Let's assume that we are going to analyze this vector a little bit here. Okay, so this is the magnetic field strength, or the direction of the magnetic field, which is towards north. Now, as for, let's say, for the direction of the motion here, or the speed here, of course, this is going to be analyzed to two components. One of them is going to be what? We can say V sine theta, okay? My bad, not V sine theta. V cosine theta Okay, because the angle is with the y-axis or with the north, so this side, of course, is going to be v cosine theta. Okay, and then the other side here, which is basically x-axis, so it's going to be v, because the angle is over there, so it's going to be v sine theta here. V sine theta. Now, forget the cosine and sine here. Let me ask another question. Do you think there will be any magnetic force if the direction of the motion were the same as the direction of the magnetic field strength? We said earlier, or in the previous question, when these two are parallel to one another, of course there will be no magnetic force here. So this, we can say this component of the force will act or cause no magnetic force here. So in another word, we're not going to take this component right here. So what, oh, by the way, we can erase this one now because we've already divided into two, or analyze this one to two components. So we have two components. One component on y-axis, the other one is on x-axis here. All right, so my question was, again, if these two were in the same direction, will there be any magnetic force on the charged particle? The answer is no. So this component will cause no force here. What about the other component? Of course, this component is perpendicular. Let's go back one more time. I think we went too much. All right, let me go back to this. Let's erase this part right here. So erasing this. Now, but this component right here, you can see that it is perpendicular to the magnetic field. So this component is the component that causes a magnetic force, let's say, or allows the magnetic force to be applied on this charge right here, because this two makes them perpendicular to one another. If that is the case, now you can align your hand just like in this way so that you can find the direction of the magnetic force. So based on this, we can do this. That is basically north. So magnetic field is north. Don't forget, it is a proton, yeah? So if that is the case here, align your hand with the magnetic field and then with the direction of the velocity here, or the motion, and then you can see that the force on a positive charge, the palm of my hand, that is going to be into the page. But because we're using north and south and all that, so I'll do this one. If that is the case, then of course the force must be downward in this case right here. You can use downward if it is north, south, and all that, or you can use z negative if you're given coordinates. If not, you could just use into the page. That is also correct as well. That is basically for this. And by the way, you might see some other colleagues are using this one. That is also good enough. You can use your right hand rule to do this one as well. If that is the direction of the magnetic field and this is the direction of the velocity, you can excuse me, you can use, or you can see that the force is basically into the board or into the page, or you can say downward if you're holding your hand like this. That is also correct. But I wanted to tell you that even if you're using this, the actual reason behind this is this component that where you get the force from. Okay, and this is how it is done. So basically the force is going to be downward. As for the second part or the third part, it says the proton's acceleration as it moves through the magnetic field. Whenever it says acceleration, of course, we do have a magnetic force, which we found in the first part. You just equalize it with the, let's say, Newton's second law of motion, or F equal to mass times acceleration, and then you can easily find the acceleration. Okay, now, question 32 says a proton moves perpendicular to a magnetic field that strength of this much experiences a force due to the field of this much. Calculate the following: the speed of the proton. Now, once again, the first part we've done it a lot of times, yeah? Not the exact numbers, but similar to this. So this is the reason why we're not doing this. But the second part is a bit new, which nothing, perhaps I can say, nothing new to you, but because perhaps it's the first time you sit here, we might go through this one as well. So you're using all this, or you can say magnetic force is basically equal to QVB, yeah? So you're going to find the speed in here, or the velocity, the speed basically, because it doesn't talk about the direction of the motion here. So speed equals to magnetic force Q, all right, over B. I mean, Q times B here. So this is what you're going to use. You have the magnetic force, which is basically 4.5, and then we have the strength of the magnetic field. You have this too, and this is the charge of a proton, yeah? So you already know that. You'll find the speed of the particle here. Okay, calculate the speed. And then the second part of the question, it asks us for the kinetic energy of the particle. So this is perhaps a little bit new, you haven't seen it. Kinetic energy right, equals to what? Equals to 1 over 2 mass times speed squared, let's say. Okay, so if that is the case, but don't forget, this is the mass of a proton, yes? So the speed, you just found it in the first, let's say, part. So by plugging in the numbers, you can find the kinetic energy. But don't forget, kinetic energy is measured in joules, okay? Because it is energy. Okay. Some mosaic questions. Try to solve this one because these are very, very important. All right, now, a new concept. Well, nothing new totally, yeah? But we'll go through this one perhaps maybe in a more detailed way. It says, a charge moving through a magnetic field follows a circular path. I think we've explained this one many times before, but I'll re-explain it one more time, okay? So what happens when a charge moves into a magnetic field here? So watch this. Let's say we have a magnetic field like this. Perhaps we can make it a little bit bigger here. So what do you think will happen if a charge moves into a magnetic field here? Let's make a uniform or look like more like a uniform here. So it doesn't matter which part of this field a charge is going into. Let's say if it is a positive charge here. What happens if a positive charge goes into a magnetic field, guys? Okay, can you guess what will happen? All right, now let's see what will happen. When this charge is going into a magnetic field, so this is the direction of the motion. Magnetic field is into the page. So of course it will experience a force, you can say, because these two are all perpendicular to one another. So watch this, yeah? We can say, this is a positive charge, we can say. So the magnetic field is into the page, and the motion is towards, let's say, towards the right side of the board, you can say, or x positive here. If that is the case, then this charge will experience a force upward here. So it is going to bend like this, yeah? But if it is at this point right here, yeah, so that means this is the direction of the motion now. If that is the case, so watch this again. So the direction of the magnetic field remains the same, but the motion is basically, it is upward this time. Yeah? If that is the case, look at the tip of the pen here. It is into, let's say, into the negative x, or you can say towards the left of the board. If that is the case, then of course this charge is going to move in this case. Yeah. What if it is at this point here? You can keep using the right-hand rule. Okay. So of course it is into, but then here's the direction of the motion. So you can see the force is downward. If that is the case, then of course it is going to make the electron move like this. If you're using your hand right here, you will see that it is going to be like this. So as a result, you get a circular path, or in a different way, you can say this charged particle will move in a circle inside a magnetic field, by the way. So you can memorize this. You can say if the magnetic field is into the page, and if there's a positive charge, then of course the motion is going to be counterclockwise here. But if the magnetic field were outside, then the motion is going to be clockwise. Yeah. If it is negative, once, for example, if it is negative and if it is going, the magnetic field is into the page, it's going to be opposite, quite opposite to this. But you don't have to memorize this one. Just use the right-hand rule and that's it. And one more thing. Sometimes they will give you, for example, let's say the motion of it, or it tells you that a charged particle, whether a proton or electron, is moving clockwise or counterclockwise. Okay? If that is the case, let's say an electron is moving clockwise or counterclockwise. An electron is moving, let's say, clockwise, yes? If that is the case, what would be the direction of the magnetic field? That is the only information they give you, nothing else. An electron is moving clockwise. What is the direction of the magnetic field? So giving you just this, you might get confused. You might say, what about the magnetic force? Yeah? I need that one also so that I can determine the magnetic field strength. Well, you don't need that. Do you know why? Because when they tell you that something is moving clockwise, that means basically there's a circular motion. If that is a circular motion, you can say, there is always a force directed towards the center of the circle. Center of the, let's say, center of the circular motion. So if that is the case, let's say this is clockwise direction, yeah? If that is the case, at this point right here, the electron is moving this way. So you have V, and you have the magnetic force as well, you can say. If you have this two, then of course you can easily find the third one, which is the direction of the magnetic field strength. So how would you do this one, or how would you find the direction of the magnetic field, this one here? Is it going to be clockwise? I mean, is it will it be into or out of the page, or what direction is this? So once again, at this point, here's the motion, by the way. You can now take another point. At this point, the electron is moving downward. At this point here, the electron, you can see that it is moving it is moving, let's say, to the left. At this point here, the electron is moving, you can say upward here, yes? So using this, of course, you can tell the direction. So you can take any point here, it is all the same, because the direction of the force is always perpendicular, which is towards the center here, okay? That is basically the direction. So let's take, for example, this 2 point right here. Or you can try this 2 point right there. So the same, yeah? The force is always into, but the direction, it will change depending on which location you choose. Let's call it A, B, C, and D, yeah? All right, so at point A, location A, the motion is upward, and then the magnetic force is basically towards the X positive here. So this is magnetic force in here. Okay, so tell me, what is the direction of the magnetic field strength? So once again, this is, by the way, we're talking about an electron, don't forget, yeah? So an electron is the back of your hand, yeah? Don't forget. So the force is the back of my hand, the motion is upward, so in this case, we can say the direction of the magnetic field must be into the page here, yeah? What about if I take this location right here, yeah? That is going to be opposite to that. Once again, the back of your hand, watch this. Okay, so this is the magnetic, let's say this is the magnetic force, which is over there, but then the direction of the motion is downward. I'm using it upward, yeah? So here's what I'm going to do. How about if I do something like this, yeah? So the motion is downward, you can see my thumb, the back of my hand, it is into this, so the magnetic field is still into the page. What if you try this one, right, or the above point B as well? You will see that at all points, the magnetic field strength is always into the page, let's say. Okay, so if that is the case, basically, now what equation do we use? Because we have circular motion here, you can say, we can always use this equation like the third tip that we were talking about. We will equalize magnetic force with the centripetal force, but you do know that magnetic force equal to QVB, and then centripetal force, mass times velocity squared over the radius, and then you will be able basically to find whichever the let's say the factors that they might ask you to find. Okay, so let's go through these points. I think I haven't went through this one, so let's go through them real quick. A positively charged particle moving perpendicular to a uniform magnetic field experiences a magnetic force perpendicular to both velocity and the field. Okay, and then another thing that we have, this force cause the particle to move in a circular path. And of course, this is basically called centripetal force. But I want you to be very careful here. This force that makes the object to move in a circular path, or centripetal, let's say centripetal force here, remember, this force only changes the direction of the motion of the particle. It will not affect the magnitude of, let's say, that force here, or the magnitude of the, let's say, the particle's speed or velocity here. The only thing that this force is changing is the direction, not the magnitude. Okay. So the magnetic force only changes the direction of the particle's velocity, not its magnitude. Watch this. We've learned this one before. We said if the particle's initial velocity is parallel to, or let's say parallel, has a parallel component to the magnetic field, then of course this component remains unaffected. Now let me tell you what exactly we mean by this. Okay, take a look. Okay, so we have this. Let's say we said that if this is basically the direction of the magnetic field, and if a part or charged particle is moving in the same direction, let's say B is parallel to V in this case, of course there will be no magnetic force. Why? Because these two are parallel to one another. So we've learned this one here. And we said that if this is basically the direction of the magnetic field, if the charge is moving perpendicular to this one, so you would see that there is a right angle between the two. If that is the case, then of course we will get maximum magnetic force. Why? Because B is basically perpendicular to V. This is V and this is B. So we get maximum magnetic force. Okay? Why? Because sine 90 here is, the angle is 90, and sine 90 it is 1, so you get maximum here. We have another case or another situation here. If this is the, for example, if this is the direction of the magnetic field here, okay, and then we have a charged particle, but this time the particle is moving at an angle, that's too much, at an angle into a magnetic field. So you can see, for example, the particle is moving at this, for example, direction right here. Okay, so if that is the case, what will happen? Now we can analyze this into two components here. Let's use this one. Now we can analyze this one to two components. One of the component is, let's say this is V, this is B, okay, and here's let's say the angle, okay. So of course this side is going to be V cosine theta. If that is the case, you can see at this point here V cosine theta is going to be parallel. Is going to be parallel to what? Is going to be parallel to the magnetic field. If that is the case, of course the magnetic force is going to be 0 for this component. So this component will not be affected. So if it was just a particle, it would continue moving in a straight line without being affected. What about this component of the particle here? This side is going to be V sine theta here. And you can see that this component of the velocity is perpendicular to the magnetic field. We can, yes, we'll keep it on the board. So if this component is perpendicular to the magnetic field, so we can say V sine theta is perpendicular to the magnetic field. If that is the case, then of course this causes a force in here. So we have basically two components here. One of them is parallel to the magnetic field, which will not be affected, or in another word, you can say keeps the particle moving horizontally without being affected. And another component which is going to be perpendicular to the magnetic field. And we know that whenever a charge is moving perpendicular to a magnetic field, or even a component, this magnetic force tries to make the charged particle to move in a circle. So what we get in this case, of course, we'll get something, for example, let's say something like this, yeah? Perhaps I should draw the other way. Okay, so in another word, this charged particle is going to move, for example, in a helical path. Why helical path? Because we have two components. One of them allows the charged particle to move. The other one is allows or tries to make the charged particle to move in a circle. So once we combine these two together, of course, you can get this or something like this, and this is what is called helical path. So let's summarize this real quick. If a charge is parallel, there's no force. If a charge is perpendicular, this will make the charge to move in a circle. Okay, let's say clockwise or counterclockwise. At this point, we don't care. Okay, just this is for the sake of the example now. But if a charge is moving at an angle into a magnetic field, of course, it will analyze two components. One component will be parallel, it will be unaffected, that keeps the charge moving in a straight line. The other component will be perpendicular to the magnetic field. Of course, there will be a magnetic force on the charge. This magnetic force will try to keep the charge moving in a circle. So we have a combination of moving in a circle and a straight line. So combining these two, you get a helical path, something like a coiled spring, and the charge would be moving to the right. And this is basically the result of what we get. Okay, so going through the last study tip, I don't know, I think if we have one more minute perhaps. Okay, we do. Says, study tip, if a charge, let's say if a charge moves into a uniform magnetic field at a right angle, it will move in a circular path. But don't forget, guys, remember, Will said that the velocity of the charge will not be affected, the magnitude of the velocity will not be affected, only the magnitude. But if a charge is moving parallel to magnetic field, it will move in a straight line because there is no magnetic force. But if a charge moves at any angle, let's say, between, let's say, theta is basically bigger than 0 and smaller than 90, then into a uniform magnetic field, it will move in a helical path. Okay, by the way, when we say 0 to 90, that could be, for example, 180 to 270, that is also possible, yeah, or 270 to 370, it doesn't matter, yeah, as long as the angle between any section is basically between 0 and 90, or you can say maximum. Okay, so it will move in a helical path. I want you to be aware of this one. Okay, next time, inshallah, we're going to solve some questions, or the remaining question, until we will be done with these concepts. So till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.